Hello, dear students and listeners. Today's first lecture about thermodynamics. The lecture is called Introduction to Thermodynamics. My name is Umar Shandias. I'm an associate uh, professor of Satpaif University. Well, generally, thermodynamics can be defined as the science of energy. Although everybody has a feeling of what energy is, it's difficult to give a precise definition for it. Energy can be viewed as the ability to cause changes. The name thermodynamics stems from the Greek word therme, which means heat, and dynamis, which means power or changes, which is most descriptive of the early efforts to convert heat into power. Today, the same name is broadly interpreted to include all aspects of energy and energy transformations, including power generation, refrigeration, and the relationship among the properties of matter. One of the most fundamental laws of nature is the conservation of energy principle. It simply states that during an interaction, energy can change from one form to another, but the total amount of energy remains constant. That is, energy cannot be created or destroyed. A rock falling off a cliff, for example, picks up a speed as a result of its potential energy being converted to kinetic energy. The conservation of energy principles also forms the backbone of the diet industry. A person who has greater energy input than energy output will gain weight, and a person who has a smaller energy input than output will lose weight. The change in the energy content of a body or any other system is equal to the difference between the energy input and energy output, and the energy balance is expressed as difference between energy in and out. Well, we have laws of thermodynamics, as you may know. We have three laws of thermodynamics: the first, the second, and the third one. But generally, before we discuss the topics of first law of thermodynamics, I would like to speak about where thermodynamics could be used. Well, thermodynamics means that the means and evaluates and describes uh, the changes of the heat in different forms. For example, the whole energy process, power engineering, especially heat power engineering, are based on the laws of thermodynamics, where we are using the energy of the combustion products of the heated water, air, steam, and other types of working fluids, and the changes to produce electricity in different or to produce energy in different forms. We base our the most valuable criteria for the production of energy or the for this processes are the laws of thermodynamics. If the process is is not validated by the laws of thermodynamics, the first, the second, and the third one, the process will not work. So, okay, the first law of thermodynamics is simply an expression of the conservation of energy principle, and it asserts that energy is a thermodynamic property. The second law of thermodynamics asserts that energy has quality as well as quantity, and actual processes occur in the direction of decreasing quality of energy. For example, a cup of hot coffee left on the table eventually cools, but a cool coffee in the same room never gets hot by itself. The high temperature energy of this coffee is degraded once it is transferred to the surrounding air. Which means that if you put coffee in a room, hot coffee in a room, the temperature level of the coffee will degree on that level where it be as equal as the temperature of the room. But the whole room, the room is um, much more bigger than the cup of coffee. Therefore, we can assume by the first law of thermodynamics that coffee will heat up by the uh, sum of energy of the room. but the second law of thermodynamics says otherwise. The application areas of thermodynamics, I briefly talked about it, therefore we will continue. All activities in nature involve some interaction between energy and matter. Thus, it is hard to imagine an area that does not relate to the thermodynamics in some manner. Therefore, developing a good understanding of basic principles of thermodynamics has long been an essential part of engineering education. Thermodynamics is commonly encountered in many engineering systems and other aspects of life, and one does not need to go very far to see some application areas of it. In fact, one does not need to go anywhere. The heart is constantly pumping blood to all parts of the human body. Various energy conversion occur in trillions of body cells, and the body heat generated is constantly rejected to the environment. The human comfort is closely tied to the rate of this metabolic heat rejection. We try to control this heat transfer rate by adjusting our clothing to the environmental conditions. But before we gonna start the uh, entering the world of thermodynamics, we need to go through some basic units and dimensions. Well, first of all, the system international or international system of dimensions and unit is used generally used in the thermodynamics. For example, the uh, dimension of length has the unit of meter, mass kilogram times second, temperature Kelvin, electric current ampere, amount of light candela, amount of matter mole. There is volume too, cubic meter, and the prefixes in system international units, like we generally using from 110 in a minus 9 degree, which means nano, and usually from the tens plus 9 giga. That's the generally the useful dimensions or multiples. For example, giga, mega, kilo, hecto, deca, deci, centi, milli, macro, nano. All the above and all the lower ones are not generally used in the thermodynamics because they are just going through the line of the matter uh, in a scale of the thermodynamics. Electric turbine by a wind turbine. Okay, so let's go through the example. This is the basic example. For example, a school is paying $0.12 per kilowatt for electric power. To reduce its power bill, the school installs a wind turbine with a related power of 30 kilowatt. If the turbine operates 2,200 hours per year annually at the rated power, determine the amount of electric power generated by the wind turbine and the money saved by the school per year. Well, what we must know, first of all, the relationship between the hours and kilowatt hours and the kilowatt and kilojoules. As you may know, 1 kilowatt is 30 kilojoules per second, which means that to transform 30 kilowatt to the amount of energy that is generated by the wind turbine, we need to multiply them between them. We need to multiply them. For example, 30 kilowatt and 2,200 hours, which means annually we get the amount of energy which is equal to 66,000 kilowatt hours. Then we must multiply the amount of kilowatts which is generated by wind turbine to the to the payment of 0.12, which is $7,920 annually. System and control volumes. This is the very important topic. Why? Because the systems and the control volumes are the main working processes in thermodynamics. A system is defined as the quantity of matter or a region in space chosen for study. The mass or region outside the system is called surroundings. For example, your flat, or for example, the balloon. Balloon. The environment of the balloon is called surroundings. The real or imaginary surface that separates the system from its surrounding is called the boundary. For example, the boundary of the balloon is the rubber uh, covering of the balloon. The rubber. The boundary of a system can be fixed or movable. Note that the boundary is the contact surface shared by both system and the surroundings. Mathematically speaking, the boundary has zero thickness, and thus it can neither contain any mass or nor occupy any volume in space. System may be considered to be closed or open, depending on whether a fixed mass or a fixed volume in space is chosen for study. A closed system, or just system, consists of a fixed amount of mass and no mass can cross its boundary. There is no mass can enter or leave the closed system, as shown in figure 119. But energy in the form of heat or work can cross the boundary, and volume of the closed system does not have to be fixed. If a special case, even energy is not allowed to cross the boundary, the system is called as an isolated system, which is not interesting because there is no thermodynamical process which occurs in that system. Generally, we are working with a closed system with fixed mass, and all the rest are variables. For example, the piston cylinder device shown in the figure. Let us say that we would like to find out what happens to the enclosed gas when it's heated. Since we are focusing our attention on the gas, it is our system. The inner surface of the piston and the cylinder from the boundary, and since no mass is crossing this boundary, it's closed system. Notice that energy may cross the boundary and part of the boundary may move. Yes. Piston, to be specific. Everything outside the gas, including the piston and the cylinder, is the surroundings. An open system, or a control volume, as is often called, is properly selected region in space. It usually includes a device that involves mass flow, such as compressor turbine nozzle. Flow through these devices is best studied by selecting the region within the device as the control volume. Both mass and energy can cross the boundary of a control volume. We would like to find out what happens to the enclosed gas when it's heated. Since we are focusing our attention on the gas, it's our system. Okay, so for example, when we are heating the gas, generally all gases are connected with the laws of Newton. Which is means that the pressure multiplied by the volume is equal to the temperature change, which means that in a closed system where the pressure is constant, the heated gas will increase its volume. For example, after we heated this gas, its volume became 1.5 and the mass still constant, 2 kilograms. And this we created the change in the volume. Thus we used some work. If we if we decrease the volume of the gas, we will make work too. This is the basics of the work as the form of energy. So generally that's it. This is the introduction to thermodynamics. In the following lectures we will proceed with these topics. Thank you.